nanohub.org.
Online simulation and more for nanotechnology.
Welcome back to week 1, this module 1.3, and we'll now, in this module, try to obtain an expression for the conductance or resistance. And it will be based on this picture that we developed in the last module, namely, you have a density of states, and you have these two big contacts, these reservoirs with lots of states filled with electrons up to a certain level. And that level is this Fermi level, or the electrochemical potential denoted by mu. And when you put a voltage across it, the two levels separate by an amount equal to QV, Q being the charge on an electron and V being the applied voltage. Now, why does current flow? When you apply a voltage, current will flow. And why does it flow? Well, the argument goes something like this, that this contact, the left contact, would like to bring the channel into equilibrium with itself. And into equilibrium with itself means it would like to keep the channel filled all the way up to mu1. So what this would like to do is, if you consider a level here at that energy, this contact would like to keep that level fixed. And so if it happens to be empty, it will immediately put in an electron there and fill it up. On the other hand, the right contact, when it looks at that level, says that, well, it's above my electrochemical potential, and things should only be filled up to here. And so, as soon as it sees that this level is filled up, it will pull it out. And so what will keep happening is, this contact will keep putting electrons in there, trying to fill it up, and that contact will keep pulling them out, trying to empty them. And that's why current will keep flowing, because once it comes out here, it then goes out into the external lead, and a new one comes in from here to fill up. So electrons keep getting pumped into the channel from the source, get pulled out by the drain, and then it flows in the external circuit. Now, this is a somewhat different point of view than what you'd have learned in freshman physics. You see, in freshman physics, usually the way you'd be describing it is, why does current flow? Well, because there's an electric field. And in a field, the field exerts a force on the electrons. Now, if you think from that point of view, though, it's really not very clear, because if there's a field, then all electrons should be flowing, all the electrons in the solid. Even the electrons that are down here, for example. But there is no doubt about it, and this is well accepted, that electrons down here don't contribute to current flow. What contributes to current flow is just the electrons in this range up here. Why is that? How can we understand why these electrons don't flow, don't carry any current? Well, the way I think about it is, consider those levels. This contact would like to keep it filled because it's below this electrochemical potential. So it will fill it up. Okay, but as far as the right contact is concerned, that also likes to keep it filled because it also is below its electrochemical potential. So that also fills it up. So the point is, these levels get filled, and then both contacts are happy, and so nothing more happens, you see. And so there is really no current flow here. Whereas the reason you have current flow around these energies is because the two contacts have two different agendas. One wants to fill it up, one wants to empty it, and there's really no single way that both can be happy about this. Okay? And so one just keeps filling it up, the other keeps emptying it. And so all the current flow takes place in this energy range, where the two Fermi functions are different, and as such, the two contacts have different agendas. Down here, both contacts have the same agenda, it just stays filled, nothing more happens. And this is the part that is not at all clear if you think that electrons flow because there's an electric field. Well, if it's an electric field, then of course every electron, even the ones down here, should be feeling that field. And in that case, how well something conducts would depend on how many electrons a particular solid has, which actually is not at all true. As you know, conductivity varies widely from one material to another. There are things like copper that conduct electricity very well. There are things like glass that don't conduct at all well. But if you counted the number of electrons, both have about the same number of electrons. So it's not like copper has lots of electrons and glass doesn't. Now, people say that, well, copper has more free electrons, but then that brings you to the question of which electrons are free, etc. But the real point is, the reason copper conducts well is because right around that electrochemical potential in copper, there is lots of states. Whereas if you're thinking of something like glass, the electrochemical potential would be in a region where the density of states is almost zero, so that there's hardly any states, and that is why it doesn't conduct. Okay. Now, if you want to turn this into a quantitative expression, the way we can do it is something like this. Let's start by thinking of it as if I just got one level here. Just one level, let's say. Now, of course, we have a distribution of levels, as I said, which you describe by a density of states. But supposing, for the moment, we say, let's just take one level. So the question is, what will be the current flow through that one level? So you could write it something like this. I is equal to Q divided by T, where T is the time it takes for an electron to get from the left contact to the right contact. I'll call that the transfer time. So, if an electron gets from left to right in a picosecond, then T would be a picosecond. If it's a nanosecond, it would be a nanosecond. That's T. So, the rate at which electrons get from left to right would be 1 over T, and Q is the charge on an electron, so you'd write the current as Q over T. But then, there could be electrons going from left to right as well as right to left, so I should be looking at the difference. So I should be multiplying by F1 minus F2. So F1 is the Fermi function in contact 1 at that energy, F2 is the Fermi function in contact 2 at a given energy. And so this is what the current I would expect then, if you had just one single level. Now what we have is, of course, if you look at a particular energy, how many levels do we have? Well, if you look at a certain range of energies, dE, let's say some range of energies given by dE, then the number of levels in that energy range is dE times the density of states. You see, the density of states tells you how many levels you have per unit energy. So if you consider a range dE, a small differential range dE, then the number of states is density of states times dE. Now there's one little thing here, one subtle thing that I need to put in to get it right, and that is dE divided by 2. And the argument for the 2 is something like this. That you see, this D of E tells you all these states that are available for electrons to flow. And I think of these states as sort of like lanes on a highway. So you've got this highway that connects the source to the drain. And you've got all these lanes. And the thing is, half of them are for going from north to south. The other half are for going from south to north. So when you are trying to think of electrons going from, say, south to north, you only have access to half the lanes. And the other one is the other half. So that's this origin of the 2 there. But other than that, I'd say Q over T, that's the current through one level, and then density of states times the energy range, that tells you how many levels you have, and of course the current is proportional to F1 minus F2. And if I want the total current, this is the current through an small energy range dE. Now if I want the total current, then all I have to do is integrate this all the way from minus infinity to plus infinity, all levels. Of course, the main contribution to this integral will only come from that energy range where F1 is different from F2. So you go way down in energy someplace here, it won't contribute to the integral at all because F1 will be equal to F2. Both will be 1. You go way up someplace, both are 0. Again, nothing contributes. Main contribution will come right around here where F1 is different from F2, as we had physically argued. So this would be then the mathematical expression for how you would calculate the current. F1 minus F2, and these are the Fermi functions in contact 1 and contact 2 with these two different electrochemical potentials which are separated by QV, the applied voltage. Okay. Now, this is an expression one could use in general then to find the current. Now, there's one simplification one can make for small voltages, and that leads to an expression for the current that is proportional to the voltage. What I mean by that is when you use this, in general, voltage may not increase, a current may not increase linearly with potential. But for small voltages, what one can do is, this F1 minus F2 can be written as minus partial derivative of F with respect to E times QV. Now, this isn't meant to be obvious. This is one of the things, I'll try to explain it in a minute a little better. And this is also something that we'll go through in one of the tutorials in terms of the mathematical details of exactly how this works. But if you accept this, then you see you could write the whole thing in the following form. There's the V, I can pull it out. So from here, by making this approximation, the one that I said requires more discussion, by writing this in this form, you can get to this expression. And now you see current is proportional to voltage, which means whatever is on the right here is something you could identify as the conductance, because I divided by V is the conductance. And that is, of course, the conductance. So this is then the expression for the conductance. And I want to, as I said, this step needs a little more discussion, and it will also be part of the tutorial that we'll go into. But I want to say a few words about this function and what it looks like, where it comes from. So roughly speaking, you can see that when I look at the difference between F1 and F2, remember F1 is this function, F2 is exactly the same function but lowered a little bit. So F2 looks something like this. So that's F1, that's F2. So question is, what does the difference look like? Look at the difference between the two. As I mentioned earlier, when you go way up here, it's 0. Way down here is 0. The difference is right around here. So what you'd expect is it would look something like this. It will be non-zero in this small range here. And for small voltages, that is when mu1 and mu2 are separated by an amount that is much less than kT, that is when the applied voltage QV is much less than kT, the difference can be written in terms of this del F0 del E, that's the derivative of the Fermi function times QV. And the derivative of the Fermi function basically looks something like, as you know, if you look at the derivative of this function, it's 0 up here, 0 down here, it will look something like this. And one important property of this function is that if I integrate it in energy, so what we are plotting here is minus del F0 del E, and that's an important function in its own right, in the sense that in the last module we talked about the Fermi function. This is the derivative of the Fermi function, which looks like something that's peaked right around the electrochemical potential. And the area under this curve, actually, you can show is equal to 1. Again, something we'll go over in the tutorial, that part of it. So, this is a function whose area is 1. This is the quantity that you could view as the conductance, G of E. So, the way you can think about it, the takeaway message from what we did in this module so far is that you can think of this current flow as proceeding through different energies at different levels at different energies, and at any energy the conductance is like Q squared D over 2T, where D is the density of states at that energy, T is the time it takes for an electron to get from left to right through that level. And which kind of sounds reasonable, because conductance tells you this flow of current. How well does it flow? Well, it depends on how many lanes you have on your highway and what's the speed limit on your highway and how fast electrons can get through. So if it takes a long time to get through, then you don't get much of a current. If it is short time, you get a lot of current. So conductance is proportional to that. And this integral over minus del F0 del E, you could think of as a sort of averaging procedure. That is, as if you have a certain conduction at this energy, at this energy it's a different one, here it's something else. And what you are doing is taking that conductance and averaging over this energy range according to this weighting function, whose area under that curve is 1. So, for example, if this conductance were essentially constant over this entire window, then you could have pulled this out of the integral and what is inside would have just been 1, because as I mentioned, the area under that curve is 1, and then that would be the conductance. In general then, you can think of the conductance as this quantity Q squared D over 2T, and with the reminder always that this is something that's a function of energy, and if you actually want the conductance, you should average it over energy according to this prescription. So that will then go on. Next, I'll try to explain how this view of this conductance gives us the new form of the Ohm's law as I had stated earlier.